Okay, well, so this lesson we are looking at minimal spanning trees, so exercise 2F. It is a fairly long explanation, and I will go through a lot of examples with you, only because it's probably the more, I don't want to say hard, but it's probably the hardest part of this topic. And you definitely need it once you move into critical path analysis later on. Okay, so the following exercises after today, a lot of it involves applying what you're doing in this lesson to like problems and things like that. So it is quite important. It does make it a lot easier if you have your booklet or if you have a copy of the booklet with you, because with the examples further halfway through the video, what I will ask you to do is to do the questions yourself. So pause the video, do the question yourself, and then see if we get the same answer. Okay, because that's what I would generally do with you in class. Otherwise, you're just watching me do it, and there's really no point. This is best understood through practice. Okay, and the more that you do questions like this, the easier that it will become. Okay, and you'll start to see what it is that you're actually doing. Okay, so let's start. So your learning intention for today is to determine the minimum spanning tree by using Kruskal or Prim's algorithms or by inspection. Okay, I focus and I'll only really show you that one algorithm. Okay, so I prefer Prim's algorithm. I find it a lot easier. The textbook will show you Kruskal's, so you can have a look at that one if you're interested, but you don't need to know both. Okay, so I'll just do Prim's. Okay, so let's have a look. It says, in some network problems, it is important to minimize the number and weights of the edges to keep all vertices connected to the graph. For example, a number of towns might need to be connected to a water supply. The cost of connecting the towns can be minimized by connecting each town into a network or water pipes only once, rather than connecting each town to every other town. To solve these problems, we need an understanding of trees. Okay, so we haven't really been introduced to a tree prior to this lesson. So a tree is a connected graph that requires no cycles, multiple edges, or loops. The diagram below shows two network graphs that are trees and one network graph that is not a tree. So basically every vertex in a tree needs to be connected only once. Okay, so if you look at these in this graph 1, they all are connected to each other in some form. You can get to each of them, but there's no need to double connect them. You don't need to do it multiple times. Okay, so both of these, each vertex is only connected through one edge. Graph 3 has what a tree cannot have. It cannot have a loop. It cannot have a cycle, so where you go around and come back to where you started. And you can't have an edge where you have two paths connecting the two vertices. Okay, if it has that, then it's not a tree. Okay, so since graphs 1 and 2 are trees, they are connected and have no cycles, multiple edges, or loops. Graph 3 is not a tree. Okay, and we discussed why. Now, what's below is really important. So for trees, there is a relationship between the number of vertices and the number of edges. So graph 1 has 8 vertices, if you count it, and 7 edges. Graph 2 has 11 vertices and 10 edges. So in general, that's your rule. A tree with n vertices has n minus 1 edges. So for every tree diagram, the amount of vertices you have, if you subtract 1, it'll tell you how many edges you should have. Okay, and that will work for all of them. All right, now a spanning tree. Every connected graph or network diagram will have at least one subgraph that is a tree. If a subgraph is a tree and if that tree connects all of the vertices in the graph, then it is called a spanning tree. An example of a spanning tree is shown opposite. There are several other possibilities. So there's other ways that you can connect, all of these vertices, okay, so that they're only connected once. So for example, I didn't have to have this one, I could have had that side. I didn't have to have this, I could have had that, okay. If there's no values on it, so later when we're looking at minimum spanning trees, there are better trees, but in this case it doesn't matter as long as the vertices are all connected only once, okay, and that's what makes it a tree. So within a network diagram, so even if it has circuits and loops and things like that, within it, over the top of it, you can still draw a tree, a spanning tree. Okay, so there's those main points in that purple box. All right, let's have a look at example 11. It says find two spanning trees for the graph shown opposite. So I'm going to use two different colors just to highlight that. Okay, so 2 different ways in which I can connect these vertices, and there's probably more than 2, but there is more than 2. Okay, and so remember, we are not using any vertices more than once. So I can do a really easy one. 1, 2, 3, 4. Okay, so that one would look something like this. You've got your A, B, C, D, E. They would all be connected. Okay, so that's one option. We could go with, let's go with green. We could go like this. You can cross. You just don't touch the same corner twice. So that's another one. Okay, where you've got D, C, so they're again all connected in some form. Okay, and there's a few more that you could definitely include. Okay, so I'm not going to keep going. Alright, so that's just an example of 2 spanning trees. Now, a minimum spanning tree, this is what's important. So for a weighted graph, so remember that's a network graph that has numbers on the edges. It is possible to determine the length of each spanning tree by adding up the weights of the edges in the tree. For the spanning tree to the right here, this orange one, if I added all of those edges, I would get 22 units. A minimum spanning tree is a spanning tree of minimum length, so the shortest length that you can use to connect those vertices. So that would be, let's say you were working in the construction and you were designing, I don't know, the piping for a particular building or something like that, and you wanted to work out the shortest way you could connect all of the points. That would be really beneficial because financially you'd be spending less on your materials. Okay, so it would be beneficial for you to work out what is this. I'm sure you could connect all those points using a whole different a whole range of different trees, but the minimum one is the shortest amount of pipe. Okay, same with electrical if you're doing lights. A good electrician would use less wiring to connect all their lights because obviously it's going to cost them less. Okay, alright, so that's what our focus for today is, a minimum spanning tree. So the tree that uses the smallest amount of units, okay, to connect all those vertices together. Now, Prim's algorithm is the algorithm that we can use to find a minimum spanning tree. Okay, now I'll go through these steps and read them to you. Then we're going to do lots and lots of examples. Okay, so it says, number 1, you choose a starting vertex, any point on your network diagram. Okay, you inspect the edges starting from the starting vertex and choose the one with the lowest weight. So, and if there are 2 that have the same weight, doesn't matter which one you pick, you just pick one of them. Now you have 2 vertices and 1 edge. So you have to inspect all of the edges starting from both of those vertices that you have so far and choose the edge with the lowest weight. And if any of those edges would connect you back, so like a circuit, you ignore those edges. Okay? And then you keep doing that. So that might be a little bit confusing. I'm going to show you. This really helps. You have to draw the diagram. You cannot do these in your head. And I would suggest you use a highlighter. Okay. So it says here, apply Prim's algorithm to find the minimum spanning tree for the network graph shown on the right. Calculate the length of the minimum spanning tree. Okay, so let's find it first. What you want to do is start on any vertex. Okay, so I will pick, I don't know, that one. Okay, from that vertex, I want the shortest edge that is connected, so that one. Now I have 2 vertices. So from those 2 vertices, I want the shortest edge. So I've got 6, 7, 6 or 5. So I'm going to connect 5. Okay, now from F, E and C, I want the shortest one. So I've got 8, I've got 3, I've got 6 and I've got 7. So I'm going to go 3. Okay, so I'm looking at the end vertices. So from D and from F, I have 6, 5, 7, or 6. So I want obviously 5. Okay, so my 2 open edges vertices are now still F and A. So I can choose from 7, 6, and 2. So obviously 2. Now, because all my vertices have been hit once, I'm done. Okay, and I can check that I've done it correctly because I've got 1, 2, 3, 4, 5, 6 vertices. Oh, that's so thick. And I have 1, 2, 3, 4, 5 edges. So I know it's correct. So you can always double check your minimum spanning tree. And I can visually see that I have included all of those vertices. Now, To find the length of the minimum spanning tree, I need to add all of those sides together. So 2 plus 5 plus 3 plus 5 plus 2. If I add them together, I will get 17 units. Okay? Alright, so you can get other spanning trees, but if you're not getting 17 as your total, then it's not obviously not the shortest, it's not the minimum, and it's wrong. Okay, so it's not, it has to be the minimum, it has to be the shortest length. Sometimes you can have two that give you that same 17 units, depending on the diagram, and that's fine then, because you can have two minimum spanning trees of the same value that are not the same tree. Okay? Alright, now these are the following examples of the ones that I wanted you to pause them, try them yourself, and then compare your answer with mine. Okay, so the first example is draw one spanning tree for the network shown, calculate the weight of the spanning tree. So it doesn't specify to do the minimum spanning tree, but we may as well, because generally you're not going to be asked to find a spanning tree unless it's the minimum. Okay, that's the whole purpose of it. So let's do this for the minimum. So pause and give it a go, and then when you're done, you can press play again. Alright, so let's have a look. I'm going to start with any vertex. I'm going to start down here. So from that vertex, which is my shortest, that one there. So from here and from here, I've got 5, 4, 7, 5. So I'm going to go to 4. So from here, I have 6, 1, 3, and 2. And I also have 5, so 1. And sometimes you will need to go back and add other edges that have been missed because it didn't quite work, which is fine. Alright, so I've got 2 and I've got 3, so I'm going to go to 2. Okay, now I've still missed a whole lot, so I need to go back. I'm going to go back to here. So 1's already been done, 3 and 2, I'm going to go down to 2. So from this corner to this corner to this corner, my shortest is that one there. So that's that covered. And then up here, I need to actually include both of them. They're both equal, but I need both of these vertices. Okay, so your minimum spanning tree should look something like that. Now, calculate the weight. So it's going to be 2 plus 3 plus 1 plus 3 plus 2 plus 4 plus 2 plus 2. Let's count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 6, 7, 8. So I've got 8 edges, and just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So we're good. Add them together. So 5, 6, 11, 15, 16, 19. Have I added all of them? $19 is the weight of that spanning tree. units. Okay, sorry, my pen's playing up. Okay, so that's example 15. All right, example 16. Apply Prim's algorithm to find the minimum spanning tree for the network below, or on the right it says, but below. So we'll start here. Choose my shortest. 6, 7, 6, 5. I'm going to go with 5. So now I've got 8, 3, 6, 7, 6. I'm going to go with 3. So I've got 6, 5, 7, 6. I'm going to go with 5. And then from there I'm going to go to 2. And now they're all connected. And let's find the weight. So 2 plus 5 plus 3 plus 5 plus 2, which is 17 units. And I should probably double check. 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5, 6 vertices. Okay, perfect. Alright, next one. I'm going to start here, go that way. So 100, 90, 120, so I'm going to go 90. So 140, 200, so I'm going to go 100. 100, 70, 90, so I'm going to go 80. Then I'm going to go 70, but I still need to connect these. So the shortest way will be down there, and the shortest one for there, well, it's only one option. Okay, so if I add all of those together, I'm adding 100, 70, plus 80, plus 100, plus 90, plus 90, plus 200. Okay, so that, let's just add them up. So we've got 0, 90, 5, 730 is my minimum spanning tree. Okay, 730 units, because we don't know what it's representing. Okay? Sorry, that's not very nice. Okay, next one. It says the minimum spanning tree for the network above will include the edge that has a weight of. Okay, so let's do the minimum spanning tree first, okay? And then we're wanting to see which of these edges below are included in the minimum spanning tree. So we don't have to really worry about them until we've done our tree. So I'm going to start from this corner, shortest, 2, 8, 3, I'm going to go there. Now I can go 7. Well, there's no point going back to 3. So I can go 7, 8 or 9. I'm going to go 7. Now I've got 9, 8, 4, 6, so I'm going to go 4. From here, I got 10, 8, 5 or 9. I'm going to go down to 5. Now down here I'm done. There's no point using this edge here because it'll close it. So I'm going to go back to these two, and my shortest, again there's no point doing that because it's just going to close it. So I need to include the shorter one, which will be this one there. Okay, so that is your minimum spanning tree. So now let's check which ones are included. Is 3 included? No. Is 6 included? No. Is 8? No. Is 9 included? Yes. And then double check the last. Always check all your multiple choice answers. And 10 is not. Okay, so therefore the answer is D. Okay, number 19. For the network above, the length of the minimal spanning tree is. Alright, so let's start from, pick a corner, start from here. 8, now 9, 8, 10 or 18, well obviously I'm going to go with 8. So I've got 9, 5, 2, so I'm going to go 2. I'm going to go to 3. So I can go 5, and I've got that 5 up there. Go to 4, and we're all connected. So we're done. Okay, so let's add them up. Let me start from here. 8 plus 8 plus 5 plus 2 plus 3 plus 5 plus 4. So 16, 21, 23, 26, 31, 35 units. Okay, it's that one. This one's tricky. I like this question, but it is a bit confusing. There are a couple of different ways that you could do it, okay? So I'm going to go one way and then I'll show you the other way that I used to do it, okay? So the minimal spanning tree for this network below includes 2 edges with weightings X and Y. So these 2 edges have to be included, okay? So let's do the minimum spanning tree, and let's make sure that those edges get included. Okay, I'm going to change the color just so that you can follow what I'm doing. I'm going to start from here. Okay, so that's my shortest. 6, 1, 6. I'm going to go up here. I have to go here. Now, X, this edge is already included. We have to include that one. So whether we know that it has to be smaller or equal to 6. Okay? So that one has to be included. Alright. From here, 5 or 3, so obviously 3. Y has to be included. So it's that one there. And then we've connected them all. Okay? They've told us that the minimum spanning tree is 19. So what I know is that X plus Y plus 3 plus 2 plus 1 plus 5 equals 19. Okay, so X plus Y, so 5, 10 plus 11 equals 19. So X plus Y using algebra has to equal 8. So first thing we can do is eliminate. 7 plus 1 equals 8. 5 plus 2 equals 7, so it can't be B. 5 plus 3 equals 8, so it could be that. 5 plus 4 equals 9, can't be that. 5 plus 6 is 11, so it can't be that. So it's A or C. Now let's go back. If so let's go with option 1. So if, and the reason I'm going to do that is because y equals 7. If this was 7, and I was on this edge, so I would have had that edge, would I have included this, or would I have, use the pointer, would I have included that as my shorter edge, or would I have gone back and used one of the 6s? I would have used one of the 6s. So that's how I know it can't be A. Therefore, it has to be C. Okay? Even though X was a 1, so if that was 1 or if it was 3, when I got to here, regardless, 1 or 3 was shorter. So that doesn't really help me decide between them, but that 7 does. Okay, so that's one method that you can use to find out that it's the combo of 3 and 5. Okay, another thing you could do is you could also just eliminate, that's probably the best way to do it, is the way that we have done it. Another way you could do it is you could also say, let me just redo the whole question with the other method in case you did it another way. Alright, so, actually that was silly because you probably want those notes. Alright, I'm going to call this method 1. Let's go method 2 and I'll do it in a different colour. Okay, so method 2. What you could have done was do the tree as we did. Okay, so we can start from anywhere, but where do we start? We'll start from the same place. So shortest, shortest, shortest. Now, to include X, you would want the Y to be something, it wouldn't be 6 and it wouldn't be 7. So we know it would be one of these. So it would be B, C, or D. Okay, so we would definitely give this value here a 5. Okay, so if that's a 5, continue going. So we've got the 5, we went to the shorter edge, and then we're going to include this. Okay, so we can go to our minimum spanning tree and include all our numbers and say, okay, so I've got 5 plus 1 plus 2. We called X 5. Okay, plus 5 plus 3 plus Y equals 19. Okay, because they told us it's 19. Add these all together. So 6, 7, 8, 9, 13, 16 plus Y equals 19. Minus 16 minus 16, Y equals 3. So that's another way that you could go decide that the answer is C. Okay? So you can use either method. It is just problem solving, so whichever way makes more sense to you. Okay, I'm not really, I can't decide which one's simpler or better. Okay, both of them work. Okay, so that's example 20. Let's have a look at example 21. It says, James, Dante, Talia, and Chanel are 4 children playing a game. In this children's game, 7 posts are placed in the ground. The network below shows distances in meters between the 7 posts. The aim of the game is to connect the post with ribbon using the shortest length of ribbon. This will be a minimum spanning tree. So it says draw a minimum spanning tree for this network on the diagram below. Okay, so start at a corner. I'm going to start here. Go with a shorter one. So from there, 5, 3, 4, 6, I'm going to go to 3. From here, 5, 3, 2, 3, 6, I'm going to go here. I'm going to go to 2. Okay, if I use this 3, it takes me back to the original, so that's bad. Don't want that. So that means that 3 would be my next shortest. And then my shortest from here, with this 3 would close it, so don't include that, would be 4. Okay, and that would create my minimum spanning tree. So it says determine the length, so let's add those edges together. So 2 plus 3 plus 2 plus 3 plus 2 plus 4. So 5, 10, So it equals 16 units. And these are exam style questions. So in your upcoming exam, you would get questions similar to the ones we're looking at, definitely. Alright, last one. So the vertices of the graph above represent 9 computers in a building. The computers are to be connected with optical fiber cables, which are represented by edges. The number on the edges show the cost in hundreds of dollars of linking these computers with optical fiber cables. Based on the same set of vertices and edges, which one of the following graphs shows the cable layout in bold that would link all the computers with optical fiber cables for minimum cost? So let's find the minimum spending tree. Start here. Well, you can start wherever you want. 3 would be my shortest. From those 2 edges, 3 would be my shortest again. Then I'm going to go to 2. So from there, 3 would be my shortest. So I can go to any of the 3. I'm going to go to that one. Then from those edges, I've got 5, 6, 5, 5. I'm going to go down there, pick any 5. Okay, remember if there's more than one, you can include any of them. Then I've got 4, 5, 6, or 5 as an edge. I'm going to go to 4, go to 2, and then go to 3. So that's what my minimum spanning tree should look like. And then going down here, let's pick... Ooh, I've actually made a mistake. I just realised I used this 5, but this 3 would have connected me on a shorter distance. So let me go back. Where did I make that mistake? Yeah, that was silly. From here, I can still use this edge. I don't need to be using that 5 because it will limit me down 2. So then continue it on. Okay? Alright, so let's check if that matches up any other diagrams. Yes, it does. It matches with A. So your answer for that one is A. And it didn't ask you to find the minimum cost. Okay, that's done. I'm really sorry for the long video. Hopefully you found it helpful and you have paused along the way and tried those questions. If you haven't and you just watched, that's okay. Maybe now, before you do the exercise, go back and try doing those questions on your own without looking at your notes and see if you get the same answers. As I said, with these questions, you have to draw the diagrams, so make sure that when you are looking in or doing the exercise, you're drawing the diagrams and then answering them. Okay? Let me know if you need any help. Thank you.